Welcome back to the physics astronomy session. Next we'll hear about analysis on heterogeneous clusters with HTCdaskgateway by Elise Chavez from the UW-Madison. So go ahead.
So hi everyone, my name is Elise Chavez. I am a PhD graduate student from UW-Madison, and I work on high energy particle physics on the CMS. We are going to be talking about enabling innovative analysis on heterogeneous clusters through HTCdaskgateway. I largely did a lot of this work with my team from Fermilab, and a lot of this wouldn't be possible without them. So big thank you to our applications team, which is Maria Costa-Fletches and Bert Holtzman, and then our infrastructure team, who is Christophe Bonat and Ed Simmons. They did a lot of work on this, so big thanks to them. So before we get started, I wanted to really go into some jargon that I'm going to be using because there's a lot of acronyms. So first we have CMS, which is compact muon solenoid. So a muon is a particle, so just think a heavy electron. And then we have solenoid, which is just a cylindrical coil that produces a magnetic field. HLHC is high luminosity Large Hadron Collider, where luminosity is it helps us understand the number of collisions that we expect, and this is related to the amount of data that we're going to record. TeV is tetra electron volt. The electron volt is a very common energy unit for high energy physics, and the tetra electron volt, so the TeV is what we typically use for beam energy. And for physical understanding of what a TeV is, it's about the kinetic energy of a flying mosquito, which I learned while making this talk, which doesn't really sound like a lot, but when you focus that down to the subatomic level, that's like focused energy on a very small scale, so it turns out to be a lot. I've already used the word Fermilab, but Fermilab, if you don't know, is Fermi National Accelerator Laboratory. It is the U.S.'s National Particle Physics Lab located in Batavia. An event is a snapshot of what's going on inside the CMS, and in our case, that's going to be a proton collision. VO is virtual organization, or VO. And these are just how we allocate resources amongst our clusters and things, and then also how we do affiliations. So for example, CMS is a virtual organization, and so is DUNE, which is Deep Underground Neutrino Experiment. And then the last one here is LPC, which is the LHC Physics Center. This is the facility we use for analysis at Fermilab. So now that we have some jargon under our belt, I wanted to give some context to the HTCdaskgateway. So we're going to talk a little bit about CMS and HLHC, and then we're going to talk a little bit about CMS analysis and the analysis facilities themselves, and then we'll talk about a specific analysis facility, the EAF, and also introduce HTCdaskgateway. So the CMS is a general purpose detector, and we use it to look for a wide range of physical phenomena. And we do that by colliding those protons and then just basically seeing what happened. You can think of the CMS as a camera. So we take sort of pictures, those snapshots or events of what happened after a collision. And then we look at those products, and then we work our way backward to see what was produced and also how they were produced and why, so that we can understand the physics of that. And if you look at the top right, this is an image of the beamline, and then also the CMS around it. And then at the bottom right, we have an event rendering from the first stable beam collision. So this is like what we would see in the CMS. And currently record about 2,000 to 3,000 events per second, and each event is about 1 megabyte. So at the end of the day, we're collecting a lot of data. But it turns out we want a lot more data so that we can have more statistics and do better analyses. And to do this, we plan to upgrade the CMS and the LHC, and particularly we want to increase the luminosity of the LHC. So again, more collisions, we want more of those so that we can have more of that data. And so our volume of data is going to increase by about a factor of 10. So for some perspective on that, we currently store about 200 petabytes of data, and we're going to go to about 2 exabytes. So it's a lot more data. And with this increase of data, there have become a lot of questions of how do we do analysis at this scale. Our current model is a sort of hurry up and wait model of analysis. So if you look at this diagram here, we have at the top, we sort of start our analysis strategy, we develop it, we prepare it, and then we prepare jobs, and we submit them, and then we sort of wait. And then we get those results back, and then at the end, we get a plot, and then we're either happy with that plot, and we're like, yay, this can go in the paper, or we're like, that's not what I'm looking for, and then we go through this whole process again, and it's just a lot of waiting. And currently that is okay, because the wait times are not terrible, but as we go into more data, we're going to have these much larger wait times, and we also have to worry about our resource allocations and things of that nature. So we have to wonder, what do we do? So ultimately, what we need to have is a fast and user-friendly way to perform analysis. And so to do this, we're going to move to more of latency analysis, where we are going to try to reduce those wait times and then also make things to make analysis more dynamic so that we can do more changes instead of just making them, submit them, and waiting for them. So in order to do this, there's sort of two sides. There's analysis and there's infrastructure. And so this is where things like COFFEE analysis and CMS analysis facilities kind of come in. COFFEE is Columnar Object Framework for Effective Analysis. This is more on the analysis side, and this is to help with easier and faster physics analysis, and it integrates industry standards. And then on the sort of both sides, they have analysis facilities. And these are platforms with a suite of tools aimed at sort of enabling sort of interactive and coherent analysis ecosystems. And we use Jupyter Hub, Kubernetes, Docker images, and Python to sort of bring this all together so that we have a way to do our analyses. A specific analysis facility is the Elastic Analysis Facility. It's a particular one that I work on. And among the analysis facilities, it's a little bit unique. It is a multi-vo analysis facility. So what we do is we serve all of the experiments at Fermilab. And we do that through specialized software and notebooks that we provide for all of these experiments. I particularly work on the CMS, and everything I talk about here is actually in reference to CMS and those batch systems. The AF is a homogeneous deployment layer in Kubernetes, and it is open to all Fermilab employees and approved users, so it is unfortunately not, you can't just log into it and use it. You would have to be affiliated with Fermilab. But if we look at this diagram on the right, in the center we have the Jupyter Hub instances for all of the experiments. On the left we have the services we provide. On the right we have our HT Condor batch systems, and you see in the bottom right you see Daskgateway. So this would be how we would connect our Jupyter Hub instances to our batch services for HT Condor, and this is where HTCdaskgateway would come in. And so now that we have introduced it, we're going to talk a little bit about what it does and what is it. But before we really get into that, I want to talk a little about Dask and HT Condor, and then I will go into the authentication problem that we face and how we solve that, and then we'll talk about more about how it works and also the features and development that we plan for the future. So Dask is a library for parallel and distributed computing. It's widely used in big data and for scalable computing. So think you have a really computationally intensive task and you would like to run that. If you just ran that on your computer, it may take forever, it may not work. And so what Dask helps you do is break that into tasks and helps those things run a lot faster. One very important thing is that it has an optional sub-package called Daskgateway, and this is how you get Dask to work on Kubernetes. So really important for us, and it was really important to HTCdaskgateway, as you can imagine by the name. And then the other thing is HT Condor. HT Condor is a software system for high throughput computing, and so it helps us submit and execute jobs on remote machines by having, and it predefines environments for that so that we can use our batch systems and do our high throughput computing. And I want to highlight this is high throughput computing and not high performance computing. This is for HTCs, not HPCs. And so this brings us to the problem that we saw. So the issue with our batch submission was that we had HT Condor, Dask, and Kubernetes trying to work together. But unfortunately, users for the Kubernetes system don't have access to the cluster backend, so we couldn't use Dask. We had to use Daskgateway. And the other issue was that Daskgateway doesn't have inherent support for HT Condor. And the other thing is it attempts the job submission from the scheduler. And so if we look at this diagram on the right, you can see that a user would try to submit a job, and then Dask, the scheduler, would start this ephemeral user and try to submit that to our HT Condor systems. And then this would not work because, one, there's no HT Condor support, and then two, the LBC doesn't know who that is. They're like, I don't know who you are, you started with credentials that I don't know. And so we had this authentication problem where we could not submit those jobs just using the bare Daskgateway. And so we had to find a solution, and it was designed by Maria Casas-Fletcher, the person I mentioned at the beginning. And so before we really get into the solution that we came up with, I did want to go over what an HT Condor submission looks like. So on the left side, we have the executable that you would run. So this is a script. In this case, this just lists some fruits that you take in from the user. And then the middle is what we call a JDL file. and you have your executable right there. That's the executable that those jobs are going to run. And JDL stands for Job Description Language, and this is a really apt name because what it does is it describes the job to HTCondor in the scheduler. And you have your log files, you can define memory, CPUs, all of that. And at the bottom you have queue, and this would be the number of jobs that you're submitting. So once we have our JDL file, you would submit that with Condor Submit, and then the scheduler should start running your jobs. So with our authentication problem, we realized we can't submit from the scheduler. We're going to need to have some sort of authentication for the user, and then also, where do we submit that? And so what we decided to do was submit it from the client notebook, so that way it has all of the right authentication for us to use. And so we took Dask.Gateway, we made a derived class, and then what we did was overrode the scale method. And what this does is it prevents the Kubernetes workers from starting, and it allows us to connect our HTCondor workers to the Dask scheduler. So if you look at the little graphic here, what we do in the scale method is we sort of obtain and set those credentials, and then we obtain any available worker configurations, either preset by us or specified by the user. And then we create an accessible sandbox where we have all of our logs go so that the user has access to those. And then we create that JDL file, and then we create our start.sh. And this is where some of the magic happens, because what that start.sh does is it starts a container, and that container will connect the Dask scheduler and the HTCondor workers. And then we take that JDL, and then we submit that from our client. So to go back to that diagram that I showed before, this is what we get whenever we actually implement our HTCdaskgateway. We have everything sort of connected. We have our client notebook, talking to our scheduler, talking to the LPC HTCondor, and everything starts to work. And so to sort of take this step by step, let's get more into what actually is going on. So we have our client here. So this is a user who's logged on. They're on a Jupyter notebook. And then they have some images. Our client image is one that we make. And then there's also some other images we use that are pre-configured by the gateway for the workers in the scheduler. And so we have this blue color here also for what is going on in Kubernetes, or OKD for us, which is an open source distribution of Kubernetes. And then we have the green here for the what's going on in HTCondor. So you would have your client log in. They are, working on their notebook. They prepared their analysis, and they would write this code that's in the top corner here to sort of instantiate our gateway, which will set up, what images, what specifications do you want, and then on the sort of scheduler side, you have your scheduler here that will, with the controller or OKD API, and that will eventually lead to a scheduler pod. And then on the other side, for the workers, we submitted that JDL, and that will go to the HTCondor SCED-D, and that SCED-D will, start up those workers, and they will be using this JDL and that start script. So these HT workers are coming up with this container that will connect them back with this line all the way back to the scheduler pod, and then the scheduler pod will connect with the client. And so now all of a sudden your user will see their workers sort of start popping up, ready to do the work for whatever you've asked them to do. And so for HTCdaskgateway, we have a few features for them. We allow them to specify some worker configurations. We have worker memory, number of cores, and also the images. We also have a way to do that with a GUI. So there's a way for them to do it in the notebook, like I just showed. And then in the top right, you can see there's a little GUI here, and this is how they can do it sort of just like in the notebook if they wanted a GUI instead. We also provide Dask dashboards available for some compatible images. You have to have certain packages to get that to work, but we make sure that works for our systems. But they have this little dashboard, and this is in the bottom right here for worker monitoring. We also have some error checks for user credentials to make sure everything is working on that end. And then also we ensure that they can only use images that are approved by CMS, because it's a little unsafe for our system if they can just put an image from anywhere. So we do make sure that they actually come from somewhere that is approved by Fermilab and CMS. And then we do have documentation for EAF users. This is only accessible to Fermilab users and employees, so this is our more extensive documentation. But we do have documentation also for HTCdaskgateway on our GitHub as well for those who want to use it like that. And so our plans for future development, we do hope actually to make the HTCdaskgateway more general. Right now it's very specific to Fermilab, We also want to make it a little specific for HTCondor. We could add, we could actually allow for some of those Kubernetes workers. Maybe we could do Slurm if we wanted to. We do have some users at Fermilab. And we do want other people to be able to use it without a lot of heavy modification. We still expect that to be needed. But on that note, we do actually have a fork from the National Center for Supercomputing Applications, the NCSA. They actually forked our repo, and they have been using it for their research notebooks that they use. So it can be done. It can be modified and used in other institutions, but we do want to make that easier for people. We also want to add more extensive error checking, because right now we have an issue where the scheduler can have an error that doesn't actually get propagated to the user, and it's like a simple error like an import error, and they won't see that. And that's unfortunate, so we do want to get that to them so that they can actually fix that and run their jobs again. The other thing we have to do is, because HTCondor isn't natively supported, we have to implement each Dask feature ourselves. And so some features native to Dask are not obviously native or native to HTCondor, for example, adaptive scaling. So we have to figure out, how to implement that for our jobs. And so we kind of wrestle with what features do we need? Do we need to add more features, because some of them are going to require a lot more work for implementation, some of them will not. So, we're wondering about that. Do we predict, or do we wait for people to ask? And then the last thing that we're sort of wondering about is our reliance on Dask Gateway. So there's been a lot of slowdown in the development of Dask Gateway, and we recently needed an update, and we had to really reach out and get them to release for Dask Gateway. So we're wondering if we should, move away from that and just start implementing everything in Dask, because that is maybe what we'd have to do anyway. But we can also hope that maybe it was just a slow time for Dask Gateway and still be able to use it. And so here we are. So we have this thing that connects us to our batch systems, and what are we doing with it? So we're going to start by talking a little bit about the transition to pythonic styles of analysis for high-energy physics, and then also I'll show you an analysis workflow with Coffee, and then describe about how we are allowing for easy user-friendly access to Python. So this move to Python actually started a little while ago, maybe like 5 to 6 years ago. We had Pyroot, which is sort of the Python integrated version of our C++ frameworks. We had Uproot, Scikit, Hep. But it's actually become a lot more popular within our community. There's a lot more people who know Python. They're using Python. The other thing, too, is we have some newer things popping up. These CMS analysis facilities are sort of newer development. And there are others. There's the AF. There is the one at Purdue. There's one at Nebraska, which is called Coffee Casa, which is also really popular. And they're motivated by HLHC analysis, and they are, because of that, Pythonic by design. So we have these more Pythonic infrastructure that we're trying to use as well. And then we're also starting with frameworks that are either Pythonic by design or integrated with Python, like Coffee in our data frame. So for example, in my group, a lot of the newer students, if not all of the newer students, are on Coffee now. They're not using our C++ frameworks. So we've really started a journey into Python for our community. So with that, let's look at what an analysis workflow in Coffee actually looks like. So this first cell here is the sort of HTCdaskgateway part. This is where you would import your HTCdaskgateway. You would instantiate it, get your cluster, and set up your client, and also scale. This is just a note again that we don't allow just any image that you want. They do have to be approved. And then you would get all of this output. So it tells you what your workers are specified, like what is their memory, what is their worker cores, and also what images you're using. It also gives you the sandbox, and you see my mouse right here. This is your sandbox that you're going to use. And then you have your link to your dashboard. And then you see this big red box that looks really scary. But this is just telling us that we have some mismatches between our scheduler worker and client images. And for the most part, if there's small differences, it will still work. You can't go between minor versions of Python. Those probably will not work. And Dask and DaskGateway have to match between those two, or it will not work. But otherwise, like for example, this will work. It'll do the jobs. So in some cases, they work really well. In some cases, you have to really work with it. But for the most part, it's just a scary box. And then you have an analyzer, a user who would start developing their analysis code. It's not really important what this is. This is just a snippet of analysis code. But they would start developing that. They would write it out, and then they would use Coffee. And this is a newer version of Coffee, so this uses task graph. So you at the top would pre-process your files, and then you would in the middle here create that task graph, and then at the bottom here you would compute that task graph. And then they would wait for their analysis to finish. This is actually a really small data set, so that's why this looks like it was really fast. These can take like hours. And so then, once they got their output, they would define their histograms, plot them, and get a histogram. And so this is sort of what our analysis is starting to look like, and this is much different than what we used to do before. A lot of it was on terminal using scripts, and so we're really moving in a direction that's way more Pythonic. So the ideal workflow would be to start small. You start with a small data set, you work locally, and then you make sure it's all working, and then you would submit that code to the batch systems. And now it's easier to do that just sort of by analysis by design. You saw that line that just said client equals client. You would just change that to a local client or the remote client, and then you can just do your workflow and then change that line, and now it's pretty easy to switch between the two, which again, before, it's mostly terminal, so you're writing scripts. So you have to write scripts to get this all to work, and then you have to change them and move them around, and it was just a lot more complex. And then I already highlighted this, but the newer copy uses task graphs, which they execute with the HTCdaskgateway Dask workers, and that has introduced some problems because task graphs are really large for our needs, but we're hoping that it will help us out in the long run because there's a lot of potential there. And then these are interactive Jupyter notebooks, so they have a lot easier UI, and it makes our analysis seem more dynamic. Coding in a terminal just doesn't feel as sort of active as whenever we're doing it with coffee in the notebooks. And then we also have those dashboards and sandbox for easier monitoring. So all of this is culminates together to provide easier user-friendly access to Python. So because we have those images that we're using with our gateway, we are enabling physicists to be able to have better control over those pipelines that they're using and introduce more of the Pythonic ecosystem to their analysis pipelines. And images in general have also helped with things like progression of coffee in our data frame. And we can do this at sort of the large scale and have collaboration images, which introduce more for everyone, like things like SciPy. We have those, and then we have on the smaller scale, you could do it on sort of the user end if you can get the image approved. And so now we have more access to that scientific Python ecosystem. Also, analysis facilities are more accessible for newer generations, so they have pre-configured environments. You no longer have to be a software and package management expert to sort of get your analysis to work, so it's a lot faster. There's a lot less C++, which can be a bonus, and then those scripts are a lot less complicated. So now we have an easy way, a user-friendly way for our analyzers to get Python. And so let's get this all together. So at the end of the day, HTCdaskgateway enables innovative analysis by bringing the HTC to the Elastic Analysis Facility, which is a huge part of HEP analysis. It allows for those job submissions, and it's flexible because of images. If our frameworks change, we can change with it because we now you just change whatever we're installing, and we can really move with R&D. And it also allows our community now to really take advantage of Python in a lot of ways that we didn't before, or just rarely did before, which is really exciting for us because there's a lot of really useful things in Python that could really help us in our analyses. Another thing is we really hope to develop HTCdaskgateway to be more general so that we can allow other institutions and industries to provide those similar services either through HTCondor or even other HTC or HPC systems that live outside of Kubernetes and need to be connected to some sort of facility. If you found this interesting or you're interested in the EAF or HTCdaskgateway in general, we did recently publish a paper and I do have a link here for that, and I'll send the slides in the Slack channel so that way you can take a look at that if you're interested in it. But yeah, thank you all for listening, and I think we'll go to questions.
Okay, so there's several questions already. First, given that you spawned your own workers, why did you need Dask Gateway? What stopped you from using HTCondor cluster from Dask job queue?
So this has to, I think, do with the fact that we're using Kubernetes. As far as I understand how it was explained to me, we needed to use Dask Gateway and not just pure Dask to be able to communicate with a Kubernetes system. So largely, I think that was really what moved us towards Dask Gateway, was just largely Kubernetes.
Okay. You mentioned that you want to make it more accessible to other HT-Condor users. Have you been in communication with the HT-Condor development team at the Center for High Throughput Computing?
Not directly, not us, but we do, we are really closely associated with them. University of Wisconsin-Madison is sort of where that is. We haven't really been in direct contact with them, but it's a really good idea for us to maybe talk with them, especially whenever we're talking about features that we would like to implement. So it's a really good suggestion.
Okay. All right, next question. Or this is a follow-up of the first. DaskGateway supports Slurm and PBS already. Have you thought about upstreaming your work to DaskGateway?
Definitely. We haven't really put a ton of thought into the Slurm side of it just yet. It's just sort of like things we're starting to think about. And we do know that there is Slurm support for DaskGateway, so we're hoping that will make our jobs easier, at least if we wanted to support Slurm. And I think the question is just, does Kubernetes throw any wrenches in there? So I think, yeah, definitely we would want to use what they've already produced.
Okay. And there aren't any other questions coming in now, but I'll give a chance for there to be one more while I ask a question about slide 24. There was a mismatch in versions between the image where the notebook was running and where the worker is running.
Yeah.
So the notebooks are running not just on random laptops, they're running on some system that you control?
Yeah, they are running at the LPC. I assume like they're on their own Kubernetes computers in the LPC, and they're sort of separate from the LPC on their own.
Okay, but they are under, users don't just make these notebook environments manually. Right?
No. You would just log in and they should spawn with on our OKD clusters.
Okay.
Yeah.
So then the question I have is, why couldn't you get the versions completely locked to the same?
So we're actually working on this a little bit. So the issue is that the worker images are coming from a place that is made by actually I mentioned Coffee Casa. The coffee team actually produces images for their systems and for generally to be used. And we use those images for our workers and our scheduler because they're smaller, and the ones we have at the client are pretty big. They're really massive. They have a lot of stuff that you need to set up an entire Jupyter Hub instance for a user, and so we don't want to use just those images on the workers because they're really big. So we use the smaller ones, and the issue is that we just are not as in sync with them as we would like to be. And so what we've actually done is we've asked them to produce images that are specific to us, that we can lock in those versions so that we can have much better control over the changes in versions, because sometimes it will release an image and it will bump up Dask or DaskGateway, or well, not DaskGateway I think, but like definitely Dask, and sometimes that throws a huge wrench in our system and it just won't work. So we've been putting a lot of thought into this and like what we wanted to do. So our plan is to get our own tagged images.
Okay. And that's, since there's no other questions, let's think.